Dear students, today we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity. Elements ਦੀ ਕਈ physical properties ਹੁੰਦੀਆਂ ਹਨ ਜਿਵੇਂ melting and boiling points, heat of fusion, vaporization, energy of atomization, atomic and ionic radii, ionization enthalpy, electron gain enthalpy ਅਤੇ electronegativity etc. ਜੋ ਕਿ periodic variations ਦਰਸਾਉਂਦੇ ਹਨ. All these properties are directly or indirectly related to the atomic structure or the electronic configuration of the elements are called the atomic properties. Since the electronic configuration of the elements are periodic function of their atomic numbers, therefore, these atomic properties are also periodic function of atomic number of elements. ਇਸ ਲਈ ਇਹ atomic properties ਨੂੰ periodic properties ਕਿਹਾ ਜਾਂਦਾ ਹੈ. These atomic properties show a regular gradation when we move from left to right in a period and from top to bottom in a group. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table and increases to the maximum in the group 17 non-metals. Likewise, within a group of representative metals, let us say alkali metals, reactivity increases on moving down the group, whereas within a group of non-metals, let us say halogens, reactivity decreases down the group. ਕੀ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ properties of elements ਅਜਿਹਾ trend ਕਿਉਂ follow ਕਰਦੀਆਂ ਹਨ? ਅੱਜ ਦੇ ਟੌਪਿਕ ਵਿੱਚ certain physical properties ਦੇ periodic trends ਬਾਰੇ discuss ਕਰਾਂਗੇ ਅਤੇ ਉਹਨਾਂ ਨੂੰ in terms of number of electrons and energy levels ਨਾਲ explain ਕਰਨ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਾਂਗੇ. But before going any further, let me discuss the learning objective of the today's lesson.
On completion of this topic, learners will be able to discuss trends in physical properties such as atomic radius, ionization energy, electron gain enthalpy, and electronegativity.
Let us take up the first one, that is atomic radius. We all know that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Do you know why? Firstly, because the size of an atom is roughly 1.2 multiplied by 10 raised to the power minus 10 meter in radius and is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. An estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value, the covalent radius of the element can be calculated. Covalent radius defined as 1/2 of the distance between the nuclei of two covalently bonded atoms of same element in the molecule. For example, the bond distance in the chlorine molecule is 198 picometer and half of this distance, that is 99 picometer, is taken as the atomic radius of chlorine. Students, forces existing between the non-bonded isolated atoms or neighboring molecules are the weak van der Waals forces of attraction. So, van der Waals radius is defined as 1/2 of the distance between the nuclei of two identical non-bonded isolated atoms or two adjacent identical atoms belonging to two neighboring molecules of an element in solid state. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometer. Hence, the metallic radius of copper is assigned a value of 128 picometer. For simplicity, today we use the term atomic radius to refer to both covalent or metallic radius depending on whether the element is a non-metal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. Have a look at the atomic radii of a few elements listed in the table shown on the screen across the periods and down a family.
Let us have a look at atomic radii in picometer of elements across the periods. That is lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. From the table, we find them to be 152, 111, 88, 77, 74, 66 and 64. Similarly, in case of sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine, we find atomic radius to be 186, 160, 143, 117, 110, 104 and 99. Next, have a look at the atomic radii in picometer down a family. The table on the screen shows the name of the atom and the atomic radius. Atomic radius of lithium is 152. That of sodium is 186. That of potassium is 231. That of rubidium is 244. And that of cesium is 262. Have a look at the other atomic radii of elements shown on the screen. Two trends are obvious. ਜਿਵੇਂ ਕਿ ਤੁਸੀਂ ਸਕਰੀਨ ਤੇ elements of the second period ਵੇਖ ਰਹੇ ਹੋ, the atomic size generally decreases across a period. ਇਸ ਨੂੰ ਇੱਕ ਗ੍ਰਾਫ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਵੀ ਵਿਖਾ ਸਕਦੇ ਹਾਂ. Have a look at the decrease in atomic radius from lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number, ਜਿਵੇਂ ਕਿ ਤੁਸੀਂ ਸਕਰੀਨ ਤੇ ਵੇਖ ਰਹੇ ਹੋ. Have a look at the increase in atomic radius from fluorine to chlorine to bromine to iodine with the increase in atomic number. Similarly, we find that atomic radius increases from lithium to sodium to potassium to rubidium to cesium as the atomic number increases. For alkali metals and halogens, as we descend the groups, the principal quantum number n increases, and the valence electrons are farther from the nucleus. ਇਹ ਇਸ ਲਈ ਹੁੰਦਾ ਹੈ ਕਿਉਂਕਿ inner energy levels are completely filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Students, noble gases being monoatomic, their atomic radius abruptly increases from halogen to the inert gases. For example, fluorine has atomic radius 72 picometer, while neon has atomic radius 160 picometer. Reason is inert gases have van der Waals radius. Secondly, in inert gases, all the orbitals are completely filled, and hence interelectronic repulsions are maximum.
Students, let us now discuss about ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, the ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. As a result, ion the size expand हो जाएगा. For example, the ionic radius of fluoride ion is 136 picometer, whereas the atomic radius of fluorine is only 64 picometer. On the other hand, the atomic radius of sodium is 186 picometer compared to the ionic radius of 95 picometer for sodium ion. Students, some atoms and ions of different elements which contain the same number of electrons but differ in the magnitude of nuclear charge. We call them isoelectronic species. For example, oxide, fluoride, sodium and magnesium ion have the same number of electrons, that is 10. Can you guess if the radii will be same or different? Yes, you are correct. Their radii would be different because of their different nuclear charges. Nuclear charge on oxide ion is 8, on fluoride ion is 9, on sodium ion is 11 and on magnesium ion is 12. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, net repulsions of the electrons will outweigh the nuclear charge and ion will expand. We will now discuss about ionization enthalpy. Do you know what is ionization enthalpy? It represents the energy required to remove an electron from an isolated gaseous atom, say X. In other words, the first ionization enthalpy for an element X is the enthalpy change delta H for the reaction depicted in equation shown on the screen. The ionization enthalpy is expressed in units of kilojoules per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron, that is, it is the energy required to carry out the reaction as shown on the screen. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. As in positively charged ion, effective nuclear charge increases, positive ion holds its remaining electrons more firmly. Therefore, more energy is required to remove another electron from positively charged ion. In the same way, the third ionization enthalpy will be higher than the second as doubly charged ion hold its remaining electron even more tightly. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted as shown on the screen.
Children, let us have a look at the variation of first ionization enthalpies with the atomic number for elements with Z is equal to 1 to 60. The periodicity of the graph is quite striking. We find maxima at the noble gases which have closed electron shells and very stable electron configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies can be correlated with their high reactivity. In addition, we notice two trends. The first ionization enthalpy generally increases as we go across a period and decreases as we descend in a group. These trends are depicted in graphs for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors. The first is the attraction of electrons towards the nucleus, and second, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electrons from the nucleus by the intervening core electrons. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. Have a look at the graph shown on the screen. You will also notice that the first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. When we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during ionization of boron is a p electron. The electronic configuration of beryllium is equal to 1s2, 2s2. The electronic configuration of boron is equal to 1s2, 2s2, 2p1. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Students, the first ionization enthalpy of oxygen is lower than that of nitrogen, although the nuclear charge of oxygen is higher than that of nitrogen. Reason is the electronic configuration of nitrogen, which is 1s2, 2s2, 2px1, 2py1, 2pz1, in which the 2p orbitals are exactly half filled, is more stable than the electronic configuration of oxygen, which is 1s2, 2s2, 2px2, 2py1, 2pz1, in which the 2p orbitals are neither half filled nor completely filled. Therefore, it is difficult to remove an electron from nitrogen than from oxygen. Look at the graph. The first ionization enthalpy of neon is highest as neon has closed shell stable electronic configuration. So it is very difficult to remove an electron from its valence shell. Children, we will now learn about electron gain enthalpy. When an electron is added to a neutral gaseous atom X to convert it into a negative ion, the enthalpy change accompanying the process is defined as electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion, as represented by equation shown on the screen. Halogen atom in gaseous state accepts electrons to form halide ion in gaseous state. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, that is the halogens, have high negative electron gain enthalpies because they can attain stable noble gas electronic configurations by picking up an electron. On the other hand, noble gases like helium, neon, argon, krypton, xenon, and radon have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. You can see on the screen that fluorine has electron gain enthalpy value of minus 328, chlorine minus 349, bromine minus 325, iodine minus 295, astatine minus 270. Electron gain enthalpy becomes more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group, as we see in case of first group elements from hydrogen to cesium, because the size of the atom increases and the added electron would be farther from the nucleus. However, electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding element. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equal to 3 quantum level for sulfur or chlorine, the added electron occupies a larger region of space and the electron-electron repulsion is much less. Students, look at the electron gain enthalpy values of fluorine and chlorine on the table. The electron gain enthalpy of fluorine is, however, unexpectedly less negative than that of chlorine. This is due to its small size. As a result of its small size, the electron-electron repulsions in the relatively compact 2p subshell are comparatively large, and hence the incoming electron is not accepted with the same ease as is the case with chlorine.
Electronegativity, a qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. Unlike ionization enthalpy, the electron gain enthalpy, it is not a measurable quantity. Linus Pauling, an American scientist in 1922, assigned arbitrarily a value of 4.0 to fluorine, the element considered to have the greatest ability to attract electrons. Approximate values for the electronegativity of a few elements are given in table as shown on the screen.
For atom of the period 2, electronegativity of lithium is 1. For beryllium is 1.5. For boron it is 2. For carbon it is 2.5. For nitrogen it is 3. For oxygen it is 3.5. And for fluorine it is 4. Similarly, have a look at the atoms of the period 3 and their electronegativity shown on the second row table. electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down a group, say from fluorine to astatine in the periodic table. Do you know how can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right, but increase down each group? The attraction between the valence electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases. On the same account, electronegativity values decrease with the increase in atomic radii as well as screening effect down a group.
Let us take one question here. Arrange the following ions in order of decreasing ionic radii: lithium dipositive ion, helium monopositive ion, beryllium tripositive ion. And the answer is, from the chart we can see that helium monopositive ion, lithium dipositive ion, beryllium tripositive ion are isoelectronic ions. Among isoelectronic ions, ionic radius decreases as the positive charge increases. Therefore, ionic radii decreases in the order helium monopositive ion has greater ionic radii than lithium dipositive ion, which in turn has greater ionic radii than beryllium tripositive ion. I hope you must have enjoyed today's lesson. I look forward to the next class. Thank you for your kind attention.